Snow. It's cold, it's white, and it's wintry. So get your shovels ready, because it's about to get frosty. Now, let's talk about snow. We learned about precipitation and the water cycle in previous episodes, where we talked about its different forms like rain, sleet, and hail. Well, snow is no different. It is also a form of precipitation, but in a different state of matter. You see, snow is made up of tiny individual ice crystals that are floating in the clouds of the atmosphere. When conditions are right, the ice crystals increase in size and eventually fall down to the ground, where they accumulate, creating the appearance of heaping white powdery ice. Now, let's take a closer look at these ice crystals. Snowflakes have a hexagonal or six-sided pattern, often forming intricate formations. Their size and shape usually depend on the temperature and the amount of water vapor present during their formation. Ice crystals form at temperatures of -40 degrees Celsius. The crystals form around minute particles in the air like dust, but at lower temperatures. They are formed from frozen water vapor in the atmosphere. Snow only happens in regions of the Earth where these temperatures are possible. That is approximately latitude 35 degrees north and 35 degrees south. In areas near the equator, snow only falls in mountainous regions with elevations of about 4,000 meters or higher. Snow's texture varies and constantly undergoes change. Snow that accumulates on the ground is often dense. Some snow will eventually melt because of the changing of the seasons. As spring occurs, some of the snow will melt, while snow in polar regions, which do not melt, will turn into big ice formations and form a glacier. In elevated areas such as hills and mountains, snow accumulated may undergo a reduction of coherence due to a change in temperature. When this happens, the snow may slide and cause what is known as an avalanche. Snow affects human, plant, and animal life on the planet. It also has a significant effect on climate. Snow induces cold climates because it covers the ground with cold ice, and it also reflects sunlight and solar radiation. For plant life, the cold climate would delay their growth. For some animals, the cold climate is their cue to undergo hibernation or a deep resting state where the animal lays dormant during the winter. For humans, this is the time to adapt our clothes to the cold temperature, as well as turning on heating for homes and buildings. Snow has also been adapted by humans in recreational activities like skiing and snowboarding, which have become popular sports in themselves. The runoff water from melted snow replenishes fresh water in rivers and lakes, which in turn provide water supply and irrigation for humans. In extreme cases, heavy snow can block roads, railways, and even airports, making transportation difficult. While in mountainous snow regions like the Arctic and Antarctic, modes of transportation have been adapted to the snowy climate. Dog sleds, snowshoes, and snowmobiles are some examples of these. Tornado. Hold on to your shoes and hats, cause when this hits, you probably won't be in Kansas anymore. So in this episode, let's talk about tornadoes. also known as twisters, whirlwinds, and cyclones because of its rotational movement. Tornadoes are defined as a violently rotating air column that is both in contact with the ground and the base of a cloud. Now, let's talk about how a tornado forms. Tornadoes have a close relationship with supercell thunderstorms. Mesocyclones are a closed rotation within supercells measuring 1 to 6 miles or 1.6 to 9.7 kilometers up in the atmosphere. When the mesocyclone lowers, it takes in cool and moist air. The convergence of upward-moving warm air and the cool air causes the formation of a rotating wall cloud. When the updraft intensifies, this creates a low-pressure area on the surface. This then creates a gust of strong winds and a funnel shape forms on the ground. This process continues as the tornado has a source of warm rising air flowing inward, which powers it. That is until it reaches maturity when the cool surface winds wrap around the tornado, cutting the inflow of warm air. Finally, when the warm air is completely cut off, the tornado weakens and dissipates in the next few minutes. Like other naturally occurring phenomena like earthquakes and storms, scientists have also devised a rating scale for measuring the strength of tornadoes. It is based on wind speed and the damage they cause. Some countries use the Fujita scale, named after American-Japanese meteorologist Ted Fujita from the University of Chicago, which is as follows: F0, less than 73 miles per hour, light damage; F1, 73 to 112 miles per hour, moderate damage; F2, 113 to 157 miles per hour, considerable damage; F3, 158 to 206 miles per hour, severe damage; F4, 207 to 260 miles per hour, devastating damage; F5, 261 to 318 miles per hour, incredible damage. While in 2007 and 2013 respectively, other countries like the US and Canada have used an expanded scale known as the Enhanced Fujita Scale or EF scale, which is as follows: EFU, unknown, no surveyable damage; EF0, 65 to 85 miles per hour, light damage; EF1, 86 to 110 miles per hour, moderate damage; EF2, 111 to 135 miles per hour, considerable damage; EF3, 136 to 165 miles per hour, severe damage; EF4, 166 to 200 miles per hour, devastating damage; EF5, greater than 200 miles per hour, incredible damage. While tornado strength varies, it is still no joke. And so, here are some steps and preventive measures to take in case of one occurring nearing you. Tornadoes are fast and can strike anywhere. That's why tornado-prone areas have devised preventive measures just in case. Government authorities usually have weather prediction models in place, which can predict the occurrence of tornadoes. Houses and buildings in tornado-prone regions have basements or storm cellars designed to keep people safe in the event of a tornado. Some areas have dedicated radio frequencies for tornado warnings and advisories. If you find yourself in one, the best course of action is to seek shelter. While if there is none, the next best option is to go low in a ditch. Avoid highway overpasses as constricted space can be a subject for increased wind speed and funneling. Wind. Get ready to catch the next one. Wind needs no introduction because unless you are living in space, you can feel it in the air. Literally. Wind is defined as the natural motion of the air and other gases in the surface of a planet. Winds have varying degrees of intensity, anywhere from a gentle breeze to a strong storm. And with that, let's go check out how wind is formed. Wind occurs because of the differences in atmospheric pressure. Regions in the equator, where the climate is warmer, causes the air to rise into the atmosphere and into the polar regions. At the same time, cool air from colder regions move downward into the equator to replace that hot rising air, thus creating a continuous system of moving air. Now that we know about wind formation, let's take a look at how wind is measured. Wind is usually measured in relation to speed and direction, or what is referred to as wind shear. While this measurement is important for weather researchers, it also has applications in engineering and architecture. You see, engineers must factor the average wind shear of an area when constructing tall structures such as buildings and towers. Tall buildings must account for wind shear to safely withstand swaying in the wind. The force that wind generates is measured according to the Beaufort scale, which is named after British scientist Sir Francis Beaufort. It has 17 levels, where 0 describes calm conditions, 12 is a hurricane, while 13 to 17 are for tropical typhoons. A device called the anemometer is used to measure wind speed. In a previous segment, we also talked about the Fujita scale, which is used to measure tornado speed and damage, while hurricanes are measured using the Saffir-Simpson scale, classifying them under 5 categories. The strongest winds of a Category 5 hurricane can reach speeds of up to 252 kilometers per hour or 157 miles per hour. In other parts of the world, tropical storms and typhoon winds are measured using Japan's Tropical Cyclone Intensity Scale. The effects of wind on climate and weather are very significant because, as part of the atmosphere, wind carries heat, moisture, and other particles. Daily weather patterns are dependent on wind movement. Land and sea breeze currents are all influenced by wind. Natural processes in the atmosphere, like cloud formation, precipitation, and low-pressure areas, are also caused by wind. And because of this, wind also affects life on Earth itself. Wind is responsible for moving dust, sand, and soil particles on the surface of the planet, or simply erosion. Sometimes, the amount of eroded particles can cause the sculpting of rock formations, or even cause dust to affect agricultural products. Wind is also a great source of clean energy, all throughout human history. It has been used to drive ships around the globe, used in windmills to pump water and process grains. More modern applications of this involve harnessing wind energy with the help of wind turbines to be converted into electricity for homes and other buildings. Sun shower. This next one is sort of shrouded in myth and legend. It is somewhat rare and paradoxical. So what is it? Today, let's talk about the phenomenon called the sun shower. The sun shower is the weather phenomenon where there is rain while it is sunny outside. Quite puzzling, is it? Did you know that the term sun showers are not even found in the dictionaries of different languages? While most meteorological authorities do not have official definitions for it. So before we take a look at the science, let's explore some of the myths from around the world. Throughout many centuries, various cultures of the world have tried to come up with explanations for the phenomenon, earning the sun shower its mythical reputation. Oftentimes, people attribute it to deities or supernatural beings getting married and other interesting stories. And so, let's take a look at some myths surrounding the sun shower. In Argentina, the phenomenon happens when an old woman is getting married. In Nigeria, they say that sun showers happen when a lion is giving birth. In Bangladesh and India, sun showers are known as the jackal's wedding. In the Philippines, Capres, mythical tree-living giants, are getting married. In Bulgaria, it's bears who are getting married. In Malta, it's called Twi'led Tort, or a Turkish baby is being born. In European countries like France and Germany, the devil is getting married. In Japan, it's called Baiketsune no Yomeiri, or foxes getting married. In Sudan, it's monkeys who are getting married. And finally, in Hawaii, they call sun showers pukalani, which refers to pineapple juice, and is also the name of a rainy town. The term also means hole in the sky, and you'll see why in this next bit. And so, with all these far-fetched myths surrounding the phenomenon, now let's take a look at the science behind it. Sun showers happen when specific conditions in the atmosphere occur. In the spring or summer seasons, the varying temperatures cause columns of air to move upward, rising rapidly while displacing cool air downward. As the rising air cools, they condense and form into clouds, which, when saturated enough, release water in the form of rain. The sinking column of air may suppress clouds and create openings within them, where the sun's light is able to shine through, creating the possibility for sun showers. Another cause of sun showers are the result of wind blowing rain from clouds into less cloudy areas or cloudless areas. What this does is it brings in the water droplets to a cloudless sunny area, where people on the ground will experience rain despite having no clouds, and therefore having the appearance of rain during a sunny day. And finally, sun showers can be observed when a single rain cloud passes over a region while the sun's light is not completely obstructed from view. This will then appear to people on the ground as rain during a sunny day. Classifying storms. Once again, get ready. With an almost yearly average of 80 storms experienced all over the world, it sure is paramount that these are studied and measured. And so, that's what we are going to talk about today. The various classifications that weather scientists and researchers use all around the world. The Saffir-Simpson scale is used in the Atlantic, Eastern, and Central Pacific regions. Category 1 with speeds of 74 to 95 miles per hour or 119 to 153 kilometers per hour. Category 2, 96 to 110 miles per hour or 154 to 177 kilometers per hour. Category 3, 111 to 129 miles per hour or 178 to 208 kilometers per hour. Category 4, 130 to 156 miles per hour, or 209 to 251 kilometers per hour. And Category 5, with wind speeds exceeding 157 miles per hour, or 252 kilometers per hour. The Western Pacific region, on the other hand, uses the World Meteorological Organization Typhoon Committee Tropical Cyclone Intensity Scale. Typhoon more than 118 kilometers per hour, severe tropical storm 89 to 117 kilometers per hour, tropical storm 62 to 88 kilometers per hour, tropical depression 61 kilometers per hour or lower. In the North Indian Ocean, the scale used is the India Meteorological Department, or IMD Tropical Cyclone Intensity Scale. Supercyclonic storm, more than 221 kilometers per hour. Extremely severe cyclonic storm, 166 to 220 kilometers per hour. Very severe cyclonic storm, 118 to 165 kilometers per hour. Severe cyclonic storm, 89 to 117 kilometers per hour. Cyclonic storm, 63 to 88 kilometers per hour. Deep depression, 51 to 62 kilometers per hour. Depression, 31 to 50 kilometers per hour. While in the Southwest Indian Ocean, the scale used is called the Southwest Indian Ocean Tropical Cyclone Intensity Scale. Very intense tropical cyclone, greater than 212 kilometers per hour. Intense tropical cyclone, 166 to 212 kilometers per hour. Tropical cyclone, 118 to 165 kilometers per hour. Severe tropical storm, 89 to 117 kilometers per hour. Moderate tropical storm, 63 to 88 kilometers per hour. Tropical depression, 51 to 62 kilometers per hour. Tropical disturbance, less than 50 kilometers per hour. And finally, we have Australia and Fiji, which also uses a 5-stage category. Category 1, sustained winds 63 to 88 kilometers per hour and gusts 91 to 125 kilometers per hour. Category 2, 89 to 117 kilometers per hour and gusts 126 to 166 kilometers per hour. Category 3, 118 to 157 kilometers per hour and gusts 167 to 225 kilometers per hour. Category 4, 158 to 198 kilometers per hour and gusts 226 to 280 kilometers per hour. And Category 5, more than 198 kilometers per hour with gusts more than 280 kilometers per hour. These scales not only help us to study about tropical cyclones and their movement, but they have many useful applications. Data from these scales aid governments and concerned agencies to create contingencies and prepare for extreme weather events, and thus help mitigate disasters and save countless lives and property in the process. We are nearing the end of this episode. But before we go, let's take a quick recap. In this episode, we learned about snow, the frozen ice crystals in the atmosphere that form the precipitation of snow. Regions that have 4 seasons experience this phenomenon, as well as areas of the world with very high elevations. We also talked about tornadoes, which is a rotating mass of air and clouds that forms a funnel shape. Tornadoes form because of the interaction between warm and cool air that creates a low-pressure area on the Earth's surface. Wind is described as the movement of air and gases on the surface of the planet. Air and gases move because of differences in temperature and pressure. Wind in itself is a vital part of the planet's weather and climate systems. Its movement is responsible for all weather phenomena on the planet. We also learned about the sun shower, a naturally occurring weather phenomenon that has seemingly gained a mythical and legendary status due to the contradictory nature of experiencing rain while it is sunny. Many cultures have their own folkloric explanations for the phenomenon. But science says that sun showers may occur when rain clouds have openings where the sun's rays can pass through at an angle. And finally, we have the various tropical cycle classification systems used all over the world. The 5 scales are used in the 5 different regional basins of the planet, namely Atlantic, Eastern and Central Pacific, Western Pacific, North Indian Ocean, Southwest Indian Ocean, and Australia and Fiji. Extraterrestrial weather. Get your space suits ready, because we are taking a trip to outer space. In past episodes, we talked about the weather on Earth and how changes in the atmosphere influence the type of weather that we experience on the planet. But now, let's take it a step further. Let's talk about weather in space. Specifically, let's talk about the Sun. The Sun is the star that is at the center of the solar system. It has a distance of about 93 million miles or 150 kilometers from the Earth. Activity on the Sun's surface releases large amounts of energy, gas, and particles. These are what influence space weather. The particles released from the Sun contribute to what is called solar wind. These are made up of gas and particles originating from the Sun's outer layer, called the corona. Particles in solar wind are negatively charged, which means they have electricity. These charged particles are able to reach the Earth at speeds of up to 1,000,000 miles per hour. But fortunately for us, the Earth has natural shields in place to help minimize the effects of space weather. We actually have 2. The first is the Earth's magnetic field, and the second is, of course, the layer of gases that make up the Earth's atmosphere. Both of these act as protective barriers, which deflects most of the particles from solar winds. However, not all particles are shielded. And when some make it past the Earth's atmosphere, we get to observe some interesting phenomenon. When charged particles hit the atmosphere, it can be observed as glowing bands of light, known as auroras, which are also known as the Northern Lights. This phenomenon can only be observed in specific regions on the Earth, specifically in high-latitude regions of the Arctic and Antarctic. Sometimes, intense solar storms form on the surface of the Sun. This causes stronger solar winds, which of course carry more charged particles. During these solar storms, a solar flare may break out, which can send tons of energy throughout space at the speed of light. This is what is called a coronal mass ejection, or CME. A CME can release lots of radiation and can affect the Earth's power and communication grid. These include our communication satellites and power grids. Imagine having a blackout with no internet, cellular, and telephone communications. Wouldn't that be hard for any country? These bursts of radiation are also harmful for the astronauts who are in space. Like the astronauts in the ISS or the International Space Station. These events happen at an instant, and their effects can reach Earth within a matter of minutes. But fortunately, just like predicting the weather here on Earth, scientists have come up with ways to create models that are able to predict when a solar storm is likely to occur, which helps people on the planet prepare if such an event happens. Supercell. Once again, hold on to your hats and stay indoors. We will be talking about a unique type of storm, the supercell. Supercells are a rare type of storm that is usually associated with severe weather effects. These include strong winds, large hail, and sometimes even tornadoes. Supercells have a unique defining feature, which is the presence of a persistently rotating updraft called a mesocyclone. A mesocyclone has the appearance of a massive shelf cloud. Now, let's take a look at the formation of a supercell. Specific conditions must be met for a supercell to form. A supercell storm originates from unstable air and the changing of wind directions at different altitudes, or what is known as wind shear. This combination of factors produces a horizontal moving motion in the lower atmosphere. When the horizontal moving air meet with upward rising air, the result is a vertical rotating column of air and clouds. Supercells can be classified into three types. The first is the low precipitation supercell, or LP. This type of supercell usually occurs in dry regions where there is just enough moisture for the formation of a storm, but not enough moisture to be able to produce rain. Although LPs may not seem strong, this type of supercell often produces tornadoes and large hail. The next type of supercell is called the classic supercell. These are your typical textbook supercell with a flat updraft base and a wall cloud underneath it. This storm causes rain and hail, and if conditions are right, may also produce tornadoes at the bottom of the wall cloud. And finally, we have the high precipitation supercell, or HP. HPs are characterized by having an updraft and forward flank movement. Its wall cloud will be wrapped in rain, or what is also known as a bear cage. Because of this, HPs are difficult to observe. This type of supercell may cause extreme rain, hailstorms, and tornadoes. HPs also produce flash floods because of the high rate of precipitation that comes with it. HPs might be the strongest and most dangerous type of supercell, because aside from the extreme weather, tornado formation in an HP is difficult to observe and predict. Scientists and weather researchers use Doppler radar technology to observe supercells. Typically, supercells appear with a hook echo shape on the lower left part of the storm. This hook appendage extends southward from the storm's main core which is where hail and rain activity is located. Tornadoes also usually occur near the hook echo on the radar. Remember, if you live in a tornado-prone area, your best bet is to evacuate early when a storm warning occurs. Keep your eyes peeled and listen for storm reports over the news. Some cities and regions also employ storm cellar designs in the architecture of their buildings and homes, where people can stay during these types of storms. As always, keep safe and stay indoors. Volcano. Stand back. In fact, stand very far away. Because when this erupts, it's gonna be an awesome display of power from the very Earth itself. It's time to talk about volcanoes. A volcano is a vent or opening in the Earth's crust where eruptions made up of hot molten rock, solid fragments, and gases come from. These materials stem from the interior of the Earth. An eruption occurs when the hot molten material, or magma, rises to these vents on the surface of the Earth. Because of the immense energy of the eruption, earthquakes may occur in the vicinity of a volcano. Some eruptions may feature slow-moving sloping lava, and others just straight up violently shoot up in the sky along with gases and rock debris. Another effect of volcanic eruptions is a phenomenon called pyroclastic flow, which is described as a fluid mix of hot gases and incandescent particles. These are so hot that anything in its path becomes incinerated. Did you also know that volcanic eruptions may cause melting of snow and glaciers? When the hot ash of a volcano reaches snow in high-altitude areas, they melt. This causes the melted snow to mix with soil and start a flood of mud and snow. Ashfall is another serious effect of volcanic eruptions. Ash spewed by the volcano becomes carried in the air and falls over land and other structures. While the effects of ashfall are not nearly as fatal, accumulation of ash over housing, buildings, and crops can also cause significant damage, and it also has effects on respiratory health. While the term volcano means vent, it has also come to mean the landform created by the accumulated lava expelled from this opening. Ask anyone what they think of when talking about volcanoes, and they probably would say a mountain-like mass with a crater. A good example of this is the Mauna Loa volcano in Hawaii, which has a sloping land formation. Did you know that Mount Fuji in Japan is also a volcano? Its slopes are made up of many layers of ash and lava that have accumulated over time. Volcanoes can also occur underwater, where vents or cracks in the seafloor lead to a path for the release of lava. Many of these underwater volcanoes can be observed in Iceland. And because volcanoes give off immense energy, eruptions near coastal areas may trigger tsunamis or seismic-induced waves. These are powerful enough to cause damage to areas near the coastline. And so, how can we be safe from volcanic activity? Well, fortunately for us, there are a few ways which we can do to cope with and minimize the hazards of volcanoes.
These include the constant monitoring of active volcanoes, studying and recording past volcanic events, and monitoring local earthquake activity. Governments all over the world have established warnings and evacuation protocols in place for regions with high volcanic activity. Where do storms get their names? Now here's something you might find interesting. You've probably seen it in the news yourself. When there's a storm coming, it usually is called by a name. But not just any name. Because believe it or not, there is actually a system in place for giving storms their names. But first, let's take a quick look at the history of naming storms. In the past, there were no standard practices when it came to naming storms. Usually, people would just name storms after the places where it occurred, or the holidays or feasts when it occurred. Sometimes storms were even named after objects. It wasn't until the late 1800s to the early 1900s when a meteorologist named Clement Raggy, who was working for the Queensland government of Australia, started using first names of people to name storms. After his retirement, the practice fell out of favor. That is until its revival during the World War II era of the 1940s. So why is it important to have a naming system for storms? Well, the system aims to reduce confusion when multiple storms occur in the same region or basin. It also gives scientists, forecasters, and news outlets a simpler way of identifying and reporting storms. At present, there are 11 warning centers all over the world that officially give names to storms. They are of course assigned their own respective regions to monitor. We have in the Northern Hemisphere, North Atlantic and Eastern Pacific, Central Pacific, Western Pacific, Northern Indian Ocean. And in the Southern Hemisphere, we have the Southwest Indian Ocean, Australian region, Southern Pacific, and South Atlantic. There are also some countries which have their own specific naming conventions like the Philippines, Indonesia, and Papua New Guinea. These nations are storm-prone countries. If you look at the names from the different lists, you might notice that they are usually related in terms of local regional culture with their respective basins. For example, names used in the Northern Hemisphere include Anna, Bill, and Danny, while names used in the Northern Indian Ocean are Tej, Murasu, and Ag, just to name a few. And to add to that, regions in the Western Pacific also use international names, which are assigned by the Japan Meteorological Agency. All names are chosen from a predetermined list. Did you know? Some storm names can be retired at the request of any member of the World Meteorological Organization. This is usually done when a storm has caused major damage and fatalities. An example of a retired name is Katrina, whose namesake, Hurricane Katrina, became known as one of the deadliest and costliest storms to have ever hit the United States in 2005. Hurricane Katrina caused around 1,800 fatalities and damages costing about $125 billion. The name was officially retired in April of 2006 at the request of the US government.
St. Elmo's Fire. Now, it's about to get mythical again. So get ready to set sail as we shed some light on this magical phenomenon called St. Elmo's Fire. But first, let's take a look at the effect in action. This phenomenon can usually be observed in the mast of ship sails and the tips of an airplane's wings. A bright, bluish, purplish glow, sometimes accompanied by a buzzing sound. Now, let's take a look at the origins of the name. The effect is named after Saint Erasmus of Formia, or Saint Elmo, who was a Christian saint who lived in the 3rd century. It was said that Saint Elmo was brave and would continuously pray despite the threat of lightning during sailing. His actions inspired sailors to be brave and calm during a storm. After his death, he became attributed as the patron saint of sailors. In older times, sailors observing the phenomenon during sailing would attribute it to St. Elmo as a good omen for sailing, and thus the name stuck. And now that we know the origins of the name, it's time to take a look at the science behind the phenomenon. The phenomenon has more to do with electric charges and weather than fire, as its name would suggest. St. Elmo's fire is a type of luminous or glowing plasma that is produced by a corona discharge from a rod-shaped object such as a mast, a spire, chimney, or horn, thus producing a glowing effect. A corona discharge is the process where an electric field moves electrons around, knocking them into neutral particles. This results in the neutral particles becoming agitated into a more energetic state. Plasma occurs when there is an excess of energy that breaks up atoms in a gas. In this case, electricity during lightning can tear up gas molecules to produce plasma. Theoretically, plasma can form anywhere, but it is observed that plasma tends to concentrate near sharp points like the mast of a ship or the tip of an airplane wing. Electrons are stripped from atoms in the gas and leave behind charged ions that glow. And so, is St. Elmo's fire dangerous? Well, as luck would have it, no. It does not present any immediate danger, outside of the same risks and hazards of stormy weather. There is, however, the risk of interference and damage present for electronic equipment. However, engineers have figured out a way to prevent these unwanted effects. These include adding corona rings at the tips of towers and poles, which prevent the accumulation of the electric field. On a somewhat similar note, the study of plasma and corona discharge has led to the development of an ozone machine, which charges the air molecules to create an ozone to be used as a gas disinfectant. Corona discharges are also used in creating a charged surface, which has its applications in photocopying equipment. We are nearing the end of this episode, but before we go, let's take a quick recap. In this episode, we learned about extraterrestrial or space weather. The term is used to describe the movement of solar wind, which is composed of emissions and particles from the sun. Solar wind has a negative charge and is able to reach and affect the Earth in many ways. These effects include the northern lights and coronal mass ejection, or CME. We also talked about supercell storms, a rare but powerful tidal storm, which is characterized as a storm with a powerful rotating updraft of wind and clouds, or a mesocyclone. Supercells can cause very extreme weather effects such as hail, strong winds, rain, and even tornadoes. We also looked at volcanoes, vents or openings in the Earth's crust that are pathways for the emission of the hot molten rock and gases from underneath the Earth. Volcanoes are very powerful and cause immense damage to anything in the Earth's surface, including land formations, crops, buildings, and infrastructure, and even plant, animal, and human life. We also looked at some international and local naming practices used in identifying and naming storms. Storm names are usually selected from a predetermined list, which is based on local regional names. And finally, we talked about St. Elmo's fire, a weather phenomenon caused by lightning which creates plasma that gives off a glowing effect. It is usually observed near pointy objects on ships and planes.